Hello. So this lesson is about resonance structures and how to draw them. So first of all, we have to know what resonance structures are. So resonance structures are multiple Lewis structures. It can be two or more Lewis structures that you're showing the bonding in them in the sense that the atoms are stationary, but the electrons keeps moving. So you show the movement of electrons between them. And how does that work? So what happens is, as I said, the atoms are always in the same position. They do not change, but instead the electrons keep moving. And how does that affect the structure? So what resonance does is that it gives stability to your structure. And also, eventually, we'll end up getting a hybrid structure, which is a combination of those Lewis structures that we drew. And we call that a hybrid structure. And one important thing that happens in the case of resonance is that all the bonds that are involved in resonance are all having the same length and the same strength. All right, so let's take a look at an example, and then I'll show you how resonance works in that. So let's say something like O3. So for first thing we have to do is we have to draw the Lewis structure. So to do that, we have to count all the valence electrons. So in total, we have 18. And then we connect two single bonds to the central oxygen. So far we use 4 electrons. So we still have 14 more electrons left. Then for drawing the Lewis structure, we first have to put the lone pairs on the outside atoms to satisfy them with the octets. So to do that, we put 6 electrons on this oxygen, we put another 6 over here, and then so far we use 12 electrons. So we're still left with 2 electrons. So any extra electrons goes on the central atom. So we put the lone pair, the extra 2 electrons as the lone pair on the central atom, and this way all the electrons are used. However, we cannot just say this structure is finished because we have to make sure every single atom is satisfied with the octet rule. So we have to do a check and make sure every atom has 8 electrons after bonding. So if you look at the right oxygen, we see it exactly has 8 electrons after bonding. The left one also has 8 electrons after bonding. But then the central oxygen has only 6 electrons, so it's not satisfied with the octet. So because of that, the structure is not complete. And what we have to do is we can take one of the lone pairs on one of the oxygens away. Let's say in this case, I'm doing it from the left oxygen, and instead making it like a double bond as a shared bond between that left oxygen and the central oxygen. And now if you do a quick check, you will see all the oxygens now have 8 electrons around them, and our structure is only using 18 electrons. So I'm not touching the number of electrons. So this way I know the Lewis structure is good for this. By the way, if you don't know how to draw the Lewis structures, or I'm already trying to explain it over here, but if you want to learn more about them in details, I'm going to be tagging another video here that it shows you step by step how to draw them. Also, I'm going to be tagging another video that explains the octet rule and the exceptions. So now let's say the structure is finished, but we decided to take the lone pair from the left oxygen. But what if we take the lone pair away from the right oxygen and we do the same thing? So in reality, both of these are happening. So the double bond is one time on the left and one time on the right. So what we say is it's changing between the two structures super quick. And then, so that's why we have to draw the secondary structure as the resonance structure. So eventually we can say this structure has this molecule has 2 resonance structures. All right. Now let's see how this happens. So I want to show you the delocalizations of electrons, meaning the moving of electrons. How does resonance happen? So let's take a look at the top molecule. So that one of the lone pairs on the oxygen on the right, what it can do is now it can go back to make a double bond between those 2 oxygens. But then if you take a look at the central atom, now oxygen will have 10 electrons. So it's exceeding the octet rule, and that's not possible for it. Because of that, what you have to do is you have to take the double bond on the left one of the bonds away from it, and make it as a lone pair on the left oxygen. So this is how the bottom structure is achieved. So this is how resonance happens. So this is me showing you the movement of electrons in case if you want to see exactly what's happening. All right. Now, next thing we said is the hybrid structure which is a combination of these 2 structures. So if you want to draw the hybrid structure, what you can do is, as you can see, the single bond oxygens are always the same for them. So in terms of electrons, the lone pair and the central oxygen is always there. Each oxygen on the left, the oxygens on the left and right, they both are keeping 2 pairs of electrons. But then the third part, the double bond, is the one that is being shared between them. So I can show that with a dashed line between the 2 of them. So this is going to be the hybrid structure for the O3 molecule. All right, and then now let's compare the bonds, because I mentioned the bonds will be the same. So let's say for the bottom structure, we call the single bond oxygen oxygens A and then the other one B. So if you think about it, you might think that, okay, B is a double bond, so it definitely is shorter and stronger than A. But in reality, we just showed that the top structure and the bottom structure are constantly interchanging. So because of that, there's no difference between A and B. Eventually, you can say that both A and B have the same length and the same strength, and that happens in every resonance case. So the bonds will eventually be the same thing, and they both will be somewhere between a single bond and a double bond. Okay, so we can take a look at another example like CO₃²-. So same idea. Let's draw the Lewis structure. So first we count the valence electrons. So we have 24 electrons in total. Just keep in mind here, I'm adding 2 extra electrons because of the overall charge of 2-. So when I'm counting the electrons, I always add 2 additional electrons. So then we do the central atom connected with 3 single bonds to the outside oxygens. So we so far use 6 electrons, so we still have 18. Then we start putting the lone pairs on the outside oxygen. So 6 goes here, 6 here, and 6 here. So now we've used all 18 electrons. And then we have to check for the octet to make sure every atom is satisfied for the octet rule. So this oxygen is good. This one is good. The bottom one is good. But then if you take a look at carbon, it only has 6 electrons. So it's not happy with octet. So because of that, we know the structure is not done and we have to start making a double bond with one of the outside oxygens. So to do that, let's say I take the lone pair of the outside oxygen on the left and I make a double bond between that oxygen and the central carbon. So if we do that, now again, we're still using only 24 electrons, but every atom is satisfied with the octet. So the structure looks good. And also because the structure has a charge, we have to put a bracket around it and put the overall charge on the outside. So this is one of the Lewis structures that we can draw for this polyatomic ion. All right, so what if we take the lone pair from one of the other oxygens away and make a double bond? So let's say in the second case, I'm doing it with the right oxygen. So this is exactly one of the cases that can happen. And same thing can be for the bottom oxygen. So what I can do is I can redraw the structure with the bottom oxygen having the double bond. So what happens in reality is these 3 resonance structures, the electrons keep moving between them. So the structure is actually a combination of all 3 of these structures. So we end up having 3 resonance structures for CO₃²-. Also, let's take a look at the delocalizations of electrons. I'm going to show them between 2 of these cases. So for example, let's take a look at the bottom structure. So what we can do is we can take the lone pair on the oxygen at the bottom and start making a double bond there. And when we do that, now the carbon has 10 electrons around it. So it will be too many electrons. So because of that, I have to take the double bond away, or the pi extra, we call them pi electrons or extra electrons. So we take those electrons away and we put it as a lone pair on the right-hand oxygen. So then the structure looks like that. So this is how we can show the delocalization of electrons. Now let's compare the bond lengths and strengths. So again, let's label them as bond A, B, and C in the top structure. So you might think bond A is shorter and stronger than bond B and C because it's a double bond versus 2 single bonds, but that's not the case. As we said, because in reality, all these 3 structures are interchanging to each other, all 3 bonds will be the same exact length and the same exact strength. So eventually, they all will be somewhere between a single bond and a double bond. Now, taking a look at the hybrid structure. So as you saw in the previous page, all of them kept their single bonds. So all CO bonds had their single bonds remaining in place. However, the double bond or the pi bond was being shared between them equally. So we can show them with dashed lines. So this is one structure that kind of shows what's exactly happening in all 3 of them. Sometimes teachers are okay with you just drawing the hybrid structure, but usually they want you to draw all the Lewis structures. So just make sure what the expectation is for your school. All right, and that's it for this video. I hope you enjoyed it. If you did, please make sure to like it and subscribe for more videos I'll be posting shortly. Thank you.